Hello again. Let's talk about aromaticity and the Huckel rule. All right, so we've talked so far about benzene, which you probably knew even before this lecture that that was an aromatic molecule. But now we're going to go into the specifics of what it truly means to be aromatic. And as you are about to find out, there's more to the story than just benzene. All right, so this is basically the requirements because when you think about benzene, there's a couple structural features that should become self-evident. The first thing is that there is polyconjugation throughout all of the carbons that are present in that ring, right? So there's no single carbon in the ring that is not conjugated. All six of them are conjugated in benzenes. So that's one of the criteria. You gotta have that conjugation throughout the entirety of the ring. So that means no gaps, no sp3 carbons, no um, changing hybridization of that sort. You have to have p orbitals, in each one of these carbons, right? So basically, this is the picture I'm talking about. You have to have parallel p orbitals, which allow for full delocalization of the electrons, right? So no breaks in that conjugation. And if we do have an sp3 hybridized carbon in between, then that would be it, because that would automatically mean that this p orbital is not present there. That will break the conjugation. So you gotta have all those carbons with a p orbital, present and parallel to the rest of them. The second thing, which is very much true of benzene, is that because the carbons are sp2 hybridized, you basically have trigonal planar shape for every single one of those carbons. And what that means for the entire molecule is that the molecule is literally flat. It's planar. And you might say that, okay, well, just by having the double bonds there, that will automatically ensure that the molecule is planar. But as you're about to find out, having the double bonds doesn't automatically mean that the molecule will remain planar. Uh, all it means is that a specific carbon to which that double bond is bound is going to be trigonal planar, right? So this is not exactly guaranteed to happen. You'll see when to expect the ring not to be planar. But if it is planar, it is got one of the criteria to be aromatic, right? So now it's a full conjugation, and the ring must be planar. And then the last one is that when you count the pi system altogether, all the pi electrons that are present in that ring, um, there is a specific combination or a specific sequence of numbers that gives aromaticity to the compound, and it happens to be a count of 4m plus 2 pi electrons. This is what we call the Huckel number. And n is basically, you start with 0, 1, 2. That's not 0 electrons. It's just like the count of this entire, sequence of numbers. So if n is 0, then that means you could have 2 electrons in the entire ring system, and it would be aromatic. Right now, that might not make any sense to you, but it will in just a few moments. If n is 1, well, that will give you 4 times 1, which is 4. 4 plus 2 is 6. That's what we see for benzene, right? Because we have 3 double bonds. Each of them has 2 electrons. Altogether, you have 6 pi electrons in that system. So that's explained by, a value of n equal 1 in the 4n plus 2 criteria. If n equals 2, then 4 times 2 is 8, plus 2 is 10. So basically, we go from 2 to 6 to 10 to 14, 18, etc., etc., for the values of pi electrons present in the system. And all through this criteria is what has to be met for the ring to be aromatic. Now, I know that saying it, you have to kind of take it with a grain of salt, because you're like, okay, that seems like a pretty random number and a pretty random sequence to follow. But hopefully what I'm about to show you is going to shed some light on why the Huckel number is what it is. All right, so for this to work out, we have to consider a variety of rings. So I'm going to start with a 3-member ring, which is basically like a triangle. And basically, the way this works out. Like, there's an actual mathematical basis for what I'm about to show you, but we're not gonna really dwell at all in the math because the math is pretty hardcore. It uses linear algebra, matrix algebra, uh, through and through, and even some differential equations. So this is, let's say, a shortcut that kind of bypasses all the technicalities of molecular orbital depictions of these things. But long story short, if you have a cyclic system that you're trying to figure out if it's aromatic or not, you basically have to draw it, within a circle, and specifically you have to have one of the vertices of that ring system pointing straight down. That's the key idea. Now, the reason why that is because when it comes down to the molecular orbitals of the pi system, you will always have one molecular orbital that will be lowest in energy, that doesn't have any nodes whatsoever. But after that, as you're about to see, they're going to start popping up in sets of two. And so by positioning the polygon with one vertex pointing down will ensure that the lowest one is just the one molecular orbital, but after that you get, twos popping up through and through. So basically here you see, down here you only have one instance of touching the circle, so that we associate with one molecular orbital. Up here we have two instances touching the circle that happen at the same level, so that would mean that the next set of energy, higher energy orbitals happen to be delocalized with each other. So we have two of them at the same energy level. And for a ring that's, three members long, basically this is the molecular orbital that we will be dealing with if it is the case that each of those carbons has a p orbital for the conjugation, the polyconjugation, criteria to be met. All right, now the way this kind of looks like is that the lowest orbital has all the p orbitals in phase with each other, right? So everything on the top portion of the molecule is shaded, everything on the bottom portion of the molecule is unshaded, and it has no nodes. But when we go to the next level will have to have one node, in the positions, and that will be true for the two variations of orbitals. So there's basically two ways to end up with one node in this three-member ring. One of them is to literally have the node passing through one of the carbons. So one of the p orbitals is basically like nullified, if you will. And the other one is to basically draw a node going from left to right in the ring. So notice like here, the left orbital is it's got a shaded region on top, same thing as the right orbital here, but the one on the front is exactly opposite. And you may have noticed that I drew the orbital in the front a little bit bigger than the other ones. That's not a fluke on my part. That's actually what happens mathematically for this to work out. Because if you kind of think about it, the two orbitals on the back, by being of lower magnitude, lower size, when you combine them together, they more or less adapt to the size of this big one to kind of give you the impression that yes, the one node character is equivalent to the one node character that we see here on the left version of the orbital. All right, now another better way to kind of represent this, because it can be a little bit tedious, especially when we get to bigger rings, as to what's going on with the actual molecular orbital diagram, is to look at the orbitals from the top-down view. And so basically you can just focus on the shading on the top area of the ring only. And if we do that, the situation for the bottom ring, the one with the lowest energy, is that all the top lobes of the p orbital are, shaded, right? So I always write that as three shaded circles, right? Looking at it from the top-down view. And then for this ones, I will just have the situation of one is shaded, the other one is unshaded, and then the third one will be passing the node through it. And then for the last one, we see that the two on the back are shaded. The one in the front is unshaded. So basically, we have the node passing right in between those two, and that's basically what I'm trying to represent here. All right. So as far as the aromaticity of the ring, the easiest way to kind of tell what you gotta deal with electron-wise is to basically ensure that you only populate the molecular orbitals that fall below this middle line. The middle line is always going to be through the middle of the circle. If you fall below the middle of the line, that means that the energy, the molecular orbital that you're dealing with, is lower in energy than just a free p orbital. So this will be a stable bonding molecular orbital. And then the ones that are above the line are at higher energy. Those are your anti-bonding orbitals. If you do have orbitals that literally fall on the middle line, you can still populate those ones because they are neither anti-bonding nor bonding, so you don't really suffer from populating orbitals of that sort. But generally speaking, you want to be below this line. So what this will tell you is that you only want to have 2 electrons on this 3-member ring for it to be aromatic. And the only way to do that is to basically end up with a pi system where you basically have removed one of the electrons. Because if you think about it, this will have to have 3 p orbitals to complete the conjugation. And every p orbital brings an electron with it. And you should look at it that way, right? So 3 p orbitals, 3 electrons. If we only want to end up with 2 electrons to be fully aromatic, then we have to get rid of the 3rd electron. So this ring will have to be actually a cationic counterpart to end up with 2 electrons altogether. All right, so I'm going to continue this discussion of the rings. We're going to go all the way up to 8 rings ultimately, but I'm going to save the discussions of the next rings. Now they'll have an idea of how to look at the molecular orbitals for the next video, and I think we'll be able to move much more quickly through it. So I'll see you in the next video.